Hi, I'm Sala, and in this video we are going to discuss how to apply ratio control to a static mixing process. We may be motivated by a plant like this, in which the two inflows of a given reagent and water mixed, and the total flow and the inlet reagent fraction influence, through some tank dynamics, the levels and concentrations. In fact, we'll assume that there is a cascade control loop so that we only need to provide reagent flow and water flow set points for these two slave flow loops to follow. In the overall scheme of things, in which tank dynamics are G1 and G2, G1 describing the behavior of level and G2 defining the behavior of outlet concentration. Well, the thing is that the static mixing is the thing in pink in this figure, and what we are going to consider is what to do in this orange block in question marks, which will receive the output of a level controller, nu1, and also the output of a concentration controller, nu2, and then it must decide reagent and solvent water flows. In a previous video, we linearized this pink stuff, and based on the obtained transfer function matrix, well, actually again, because it's static, because the pink stuff is static. So with that gain, we computed the relative gain array and ended up recommending this multi-loop proposal, in which level controller output will be associated to increments on water set point, A denotes water flow, and outlet concentration controller's output will be associated to reagent flow. What we are now going to consider is ratio control and its linearization, so we can compare it with this multi-loop stuff. So let's go. The strategy of ratio control will be as follows. First, we will leave the level stuff unchanged with respect to the multi-loop option, so the level control action in increments will add the operating point and obtain the required flow of water. So next, in concentration control, instead of deciding an increment of reagent flow, we'll think as follows. First, the thing is that in our operating point, there must enter 1 liter of reagent for every 5 liters of water, or, well, for each liter of water, 0.2 liters of reagent. That's the nominal concentration. However, if for whatever reason we sense an outlet concentration which is different to the concentration set point, then our concentration controller will output an increment of ratio, increment of flow, that will be added to the nominal 0.2 to give the actual ratio to be multiplied by the water flow, giving the required reagent flow. So this is ratio control. Well, actually, these A and R will be set points to the slave cascade loops. So the actual ratio control will be as follows. We'll have this reagent flow set point to some cascade valve dynamics that will give me the actual reagent flow measured by FT1, and then our water set point in that valve dynamics will yield to a measurement of actual water flow. And then look that we have changed the intake from the set point A to the sensor FT2, to the actual measured water flow. In this way, if for whatever reason this valve saturates, it is the actual water inflow, the one that will be multiplied by the ratio to yield the desired reagent inflow amount. So we are protected, let's say, with respect to saturation in the level loop, because we have, large level errors. On the other hand, well, this cascade dynamics somehow lags FT2, so this will work only if the cascade valve dynamics is very fast compared to the level control dynamics and the associated water flow command. But well, under these considerations, this will be our proposal for ratio control. But well, this discussion is somehow similar to the one we did in a companion video discussing this two-tank case study with just common sense arguments. So what we are going now is to linearize this ratio control and to compare it to the multi-loop strategy's behavior in order to decide what's best, whether this thing or this thing. So let's go. Then on top of this slide we have the equations of ratio control. We are saying that reagent flow is ratio rho times water flow A, and that water flow is operating point A0 plus the increment of flow given by level control. This product of a time-varying magnitude rho and another time-varying magnitude A, the product of two signals, is nonlinear, so we need to linearize it. Let's go. If we define incremental coordinates, rho will be rho 0 plus increment of rho, and A will be A0 plus increment of A, but then also reagent flow nominal value operating point is rho 0 A0. So if we now carry out this product, we will have four terms, but if we subtract R0, you can pause if you wish and think on it, it's straightforward, then we get that the increment of R, which is R minus R0, is given by rho 0 delta A, rho 0 increment of water, plus A0 increment of ratio, plus the product of these two increments. But the product of two increments, if we assume that in linearization stuff increments are small, then this is a second order increment, the product of two small, in theory infinitesimal things. We can replace it by 0 when we are approximated up to first order. Then, dismissing that term, we get that the increment of ratio is rho 0 times nu1 plus A0 increment of ratio, that, well, I will call it nu2. Why do I call it nu2? Well, because if I try to understand what we are doing here, in the multi-loop block diagram, the reagent increment was some nu2 stuff, so we will identify that nu2 with this nu2. And then what does this mean? Well, if we think only in this incremental block diagram, rho 0 is 0.2, then this expression is something like this. I have drawn here the cascade saturation stuff, but okay, for the moment being you can just forget about it. But anyway, we see that indeed this is the implementation we were discussing here. So what is this block diagram? This is very reminiscent of inverted decoupling. Indeed, if we have this transfer function, well, this gain, relative gain array, advised us this pairing, so this thing, which was increment of flow using increment of water and increment of inlet reagent fraction with the reagent flow. But well, the thing is that inverse decoupling, if we wish to decouple the effect of the level flow on the concentration loop, then the decoupler is minus not chosen divided by chosen element of a given row of the transfer function. So in this case, this is minus 1 over 36 divided by plus 5 over 36, which ends up being plus 0.2. So the inverse form decoupling to cancel the level behavior on the concentration loop would imply having this 0.2 term in incremental thing from the level loop correcting the concentration loop. So this thing can be understood as a decoupling term, and this thing can be understood as a multi-loop concentration controller action. So we conclude here by realizing that ratio control is a nonlinear control strategy that multiplies some signals, of course in absolute units, because ratio control cannot be done in incremental units, but the linearization of the ratio control has this form in which it resembles this incremental block diagram in which we have a decoupling term and a multi-loop term nu2. So ratio control is somehow more exact, it's nonlinear, it incorporates this product of increments that linearization did not take into account. So if we can, it would be better to implement ratio control instead of its linearization multi-loop plus decoupling. But if increments are small, this ratio control will somehow perform more or less identically to this multi-loop plus decoupling control. And also, it's important to realize too that in this multi-loop control, this concentration controller did output something which had units dimensions of reagent flow, but in this ratio control the controller was a ratio, a dimensional ratio, so its tuning would be in theory different. But this formula tells me that actually if I tuned the concentration controller in the ratio control structure, then the multi-loop tuning that will be equivalent would be multiplying the gain of this ratio control element by A0, the nominal water flow. So in this case A0 was 5 in our operating point, so that means that if I tune a PID here for a given behavior in ratio control, then the translation to multi-loop will be the same gains multiplied by 5, adding this extra decoupling term. Good, so we conclude here. In this video, we proposed ratio control, and we did examine the relationship between ratio control and multi-loop control plus level 2 concentration decoupling, and also that the tuning of the concentration controller in ratio control multiplied by the nominal water flow gives me the tuning of the concentration control in the multi-loop strategy. Of course, given the resemblance of this thing with decoupling, then in a sequel video we will further dig into the relationship between decoupling and ratio control, in the sense that in this gain matrix we decoupled this element, but then we may be also able to decouple this thing. Understanding that and which one would be the nonlinear generalization of that decoupling will be the objective of the said sequel video. For the moment being, we end here. Thanks for watching.